complex the task, you need even more data, and it makes the entire thing expensive. Where model extraction comes in here is it uses some already existing APIs and it exploits them to learn the same task with very little or no data. So this actually creates 2 points. One is the expense for training a model is very less, but then any model that has incurred some expenses that while training it, you will face a lot more. So the thing is, you can train a new model without that expense. So that expense is rendered useless, and it's actually an issue of privacy. Yeah. So the thing is, our task is to do this model extraction attack on video classifiers in two settings. One is black box, when there is no data available, and the second one is gray box, where there is some part of the data available. That's 5% of the original data set that was used to train. So I'm audible, right? Just to confirm. Okay,
You're audible.
Yes.
great. Yeah. So let's go over the black box model extraction. Um, Yeah. So what we use here is a data-free model extraction paper. So it's a architecture that obtains state-of-the-art results in image domain. So what they do is they synthesize, since we don't have any videos or data, we use synthetically generated data using some generator. The victim is the API that we were talking about in just a while ago, and the student is the adversary, which is trying to mimic the API. So So the thing is, given any video, these two are just normal classifiers. So they will spit out some class probabilities, right? PV and PS. So the goal of the training objective you can define for the student is that it will try to minimize the probability distribution distance between the victim model and the student. So you can just pose it like PV or and PS, something like that. And the student tries to minimize this disagreement thing, and the generator will try to maximize this. So this is the minimax game they play. And also one thing to note here is that this victim model is actually a black box, so we don't have any gradients. So these dotted lines that they actually draw means that they're trying to approximate the gradient to get the back propagation to the generator. Yeah. Now we try to extend it to video since our thing is an action classification thing. For that, we use Moco GANs, which is a video generator. Uh, it generates videos using an image generator here, as well as an RNN. So this is the combination. And while training, they use two different discriminators, DI and DV. So DI acts as a critic for the image. Um, so the image generator, and DV acts as a critic for the recurrent unit, your RNNs. And the way the back propagation is done is that the loss incurred by DI only changes the weights of GI, and DV changes the weights of RNN. And that's how they train it, and that's how they get better results, is what they claim. So we use this model, and this is our proposed architecture. Uh, this is the same OGOAM thing, and we use two students. The combination of student and victim acts as the critic for. So SI is the student acting as the critic for the image, and SV and V, the combination, acts as the critic for the entire video. Since these guys, they don't take single images. Some models have fixed number of frames that they provide. So yeah, we concatenated the image, some random image from the video, and stack them together like this so that it is permissible, and then just feed it to them. The loss is similar to what we defined before in DFME, I guess, data free model extraction. And yes, and the gradients you can see here, the dotted lines, they're all approximate gradients. So one problem with this is, I guess, since we are not using any data of our own, this is very prone to mode collapse, and we have observed it multiple times during our training. So we took inspiration from InfoGANs, and we came up. So we used an information loss. So I'm sure a lot of you guys must have heard of InfoGANs. But yeah, the thing is, nobody actually used it in the data-free model extraction setting. So the thing is, so we feed out categorical data. So any generator gets a normal Gaussian noise. So in addition to that, we feed them categorical one-hot sample data, uh, one-hot sample noise, and given this noise, the intuition is that the generator must generate some similar video of that kind, and the victim should, given that video, should produce some probability which is close to ZC. And so we try to minimize the distance between them to ensure that it doesn't collapse and produce and help generator to train faster, I guess. So yeah, I think this is it for the black box setting. Now Rajat will explain the gray box setting and move on forward. Rajat, are you there? I'm audible,
Yeah,
right?
hello.
Hello.
Yeah,
Yeah. Go ahead.
thank you, Rohan. So, using the black box model ensemble as a whole was too resource intensive, and then making the model learn on synthetic data generated by the GANs was again tougher for the model to learn and intensive too. So, hence, we took a different approach for the gray box model. I'll elaborate on that approach now. So in the gray box model, since we're allowed to use 5% of the original data set, which was kinetics in this case, so we used that to train our student architecture. So just to once again clarify what is DFME approach, it is basically the model which is trying to copy the victim's functionality, which is the student model. And now coming back to our approach, we use knowledge distillation. Uh, in knowledge distillation, uh, which as the name suggests, it refers to the process of transferring knowledge from a large complex model to simple lightweight models without any major loss in the performance. So here the student classifier, which as we show in the figure is a CNN, is trained by taking a cross entropy loss between the ground truth labels which are inputted and the class probabilities which are received from the softmax function after the passing to the CNN. So in this case, we use ResNet 50, which is the student model, and for both the MovieNet and the Swinty cases that were given. And here, instead of the generator that we used in the DFME approach, we use the kinetics dataset and apply the standard cross entropy loss that I just showed you. Additionally, we also use a knowledge distillation loss. Now, why this knowledge distillation loss is important is that the cross entropy loss only takes in the labels, which give us a 0 and 1 distribution, whereas the softened logits here give the student model a more accurate understanding about the decision boundaries of the teacher. So it helps the student learn those decision boundaries better. For instance, if we see the model, if it is giving uniform probabilities across different multiple classes, or is it giving a very high probability of 0.99 for a particular class, this won't be present. This information won't be present in the labels, but it would be present in the logits, and hence the KD loss helps the student model understand those decision boundaries better. Now we scale this cross entropy loss by a factor of alpha and add this knowledge distillation loss uh, between the softened class probabilities of the student and teacher with a factor of 1 minus alpha. Now, moving on to what these softened probabilities are. So the student model has a lower capacity compared to the teacher. So because it is not state of that for that particular uh, method. So it cannot completely mimic the sharp class probabilities of the teacher model. So hence we need to do the softening of the decision boundaries of the teacher model, which we do with by introducing a temperature hyperparameter. This helps the student model from overfitting, and dividing by temperature and applying the softmax of the probabilities reduces the sharpness in the class probabilities. Coming to the results, next
Okay,
slide.
one thing I forgot actually before saying this. So here we use a, you can see this, right? So I'm sorry to
Mhm.
interrupt, but here we use a pre-trained model for the image generator. Uh, yeah, I think it's on a texture data set. Um, it's called DTD, and it just helps us to get a smarter initialization one. Yeah, you can carry on, Rajat.
Yeah, thanks. Uh, Coming to the results that we got. So, uh, just to clarify before that, the accuracies we submitted as part of our midterm report, due to a small oversight in the code, got scaled up by a factor of batch size, which was 4. So we have also tried to mention it in our report and conveyed it to the conveners too. So really sorry about that. Now, due to the heavy training time of the model and added complexity of the video domains, we couldn't match up to the SOTA that was achieved in the image domain, which is around 50%. But for the gray box, we used ResNet 50 as the student model. And in the black box, we experimented with both STAM and ResNet 50 models. We measured the accuracy by comparing the labels predicted by the student versus the teacher for each query. And a query is basically a video clip input to the model. As can be seen, we used just 300 video samples from different classes for the black box model, and we observe very low accuracies for the Swintian MovieNet architecture. But as we scale up the number of queries to around 19,000 for the gray box model, in the MovieNet architecture, the accuracy substantially increases to 27%. But due to time and resource constraint, we couldn't perform similar experiment on the other models and in the other settings. So hence we believe that maybe increasing the queries while training our black box ensemble would have helped to get better accuracies. Also, we can see here that uh, with simpler models like ResNet, gradient flows are much easier, which makes the learning faster, and the vanishing gradient issue is solved. So to conclude, we've designed and implemented the entire pipeline to apply data-free model extraction approach on video domain. We also introduced an info loss between the teacher's class probabilities and the ground truth one-hot encoded vector. So this info loss that we introduced wasn't done in any of the previous approaches. So this was a novel thing that we added. And we also implemented the knowledge distillation approach for the gray box data extraction. Generally, all these approaches need a lot of generated data, especially because it's in the video domain, to produce very good results. Hence, more augmented data would have helped our case in both the gray box and the black box scenario. Um, and then I'd just like to mention that there were so many things that we learned through the last 20 days, including multi-GPU trading, working with video GANs, and so on, to deal with this problem statement. It was quite a challenging novel problem statement, and I'm sure all the uh, all the teams had a very interesting time figuring out and brainstorming all of this. And in the end, seeing it work to a small extent was a really satisfactory feeling. So, uh, thanks. Yeah, that's it. We are open to questions.
Thank you, team two. I think it was a wonderful presentation. Couple of questions from our side, but before I jump into the questions, I would like to hear from you that what was your big challenge apart from the computation and resource related aspects? What was your big challenge that you see throughout this entire problem statement?
So, making the model. So initially, apart from even we had some GPUs, but fitting the multi GPU training, like working, it was working on single GPUs, but making it work on multiple GPUs was a challenge. We had to eventually figure out how to use half precision models and how to make the batch, how to optimize the batch size in order to make it fit on a multi GPU setting. So that was a challenge that took quite a lot of time, and making the actual the even the given there were a lot of dependency issues because GPUs that we got had some particular CUDAs pre-installed and the TensorFlow versions and everything. So we realized how important it is to have uh, all the requirements properly sorted. So now we are well equipped with that part.
Thank you for that. The second question I have is that what is your let me ask paraphrase this question differently. You have throughout all of your black box and gray box, you utilized a DFT kind of an approach. What was the decision point that led you to use only this approach and not to check any other approach?
Yeah, Rohan, you're saying anything?
Hello.
Yes, Rohan, you're
I
audible.
was
Please.
muted for a long time. I'm sorry. So I think we used two different approaches. One for gray box was an open involved the for for the black box
Rohan,
setting we
your
used this generator and
voice is breaking.
box. Hello.
It's better now.
Rohan, let me just
Better now.
paraphrase that. For the black box, I understand for the gray box you had used the knowledge distillation, but for the black box, for both of the problems, you have used the data-free approach. And I
Yeah.
see that your student model is ResNet 50 in both the cases, which comes from the image domain. Can you help me understand why this design choices or decisions were made?
Okay. So the so the
Rohan, your
can
voice is
use
breaking.
something like model.
Very, very spotty connection. Can anyone
Or
else from your team explain?
just give me a second. Me now.
Hello, Rohan.
Hello.
Yeah.
Can someone else from the team attempt?
Uh,
You still
I
can't hear me, is it?
Yeah, it's really patchy, Rohan. We are not able to hear sort of continuous sentences. It's really patchy.
I think he's now
It's
also trying,
okay.
but we are not able to hear.
Okay, so
so I'll try to
The
answer it.
focus is
Can you just repeat the question once?
But
You were asking about the design choice,
yes,
right?
yes. So I was
Yeah.
asking for the design choices, especially in the black box. You have utilized the DFD approach in both the
Yes.
cases. And in one case that I see that you have used a stamp, and in the other case I see that you have used a ResNet 50. While in the gray box, you have stuck to the ResNet 50 and knowledge distillation. So what led you to this different kind
Okay.
of approaches?
All right. So for the gray box, since we are allowed to use 5% of the data, so we wanted to not use a very heavy architecture because already we had resource training limitations. So that is why we chose knowledge distillation because training the GAN and make like getting good videos out of the GAN, which can help the models understand what the how it has to what predictions it has to give is tougher. So we wanted to just train the student model in the gray box. Hence, we use the knowledge distillation there. While choosing the for the black box model, we had to definitely use a data free extraction, a data free model because we were told we cannot use any existing data sets over there. So hence we used a GAN and created the entire assembly, which was originally where we did the literature review. We found that it was originally used for images, and we used the same. We tried to extend the same for videos by using a video GAN, and also we added a image discriminator over there to um, counter for the image part of the model.
Okay. And why did you use a ResNet 50 when you know that the
am I
ResNet?
audible now?
Yes.
Uh,
I will
Yes, Ron.
I'll just finish my question. So
yeah.
ResNet 50 is known for the images, and you have utilized that as a backbone for the video. Why was that choice?
Because we first started using with using STAM, but your voice is still breaking. We started with using STAM,
Okay.
but there was the mode we are facing the mode collapse issue. That is, the outputs were outputs of all the outputs were belonging to the same class. So when the other experiments for the gray box and black box models, we wanted to use a lightweight architecture so that there is no vanishing gradient issue and the mode collapse issue can also be solved. So we tried using ResNet and it worked well. So hence we went ahead with that. We were initially planning to
Also,
use.
just a clarification, the ResNet we used is the ResNet 3D, the 3D ResNet 50, which has previously been used for action classification, and we just modified it for our task. And the ResNet 50, we chose that over STAMP because it gave us better training in the other scenarios due to the residual connection, so the gradient flows were better.
Understood.
Judges, please wrap up the session as the 5 minutes for question and answer is over.
Okay. I think that's all from our side. Thank you, team.
Thank you.
Wonderful to learn your design choices. Good luck.
Sure.
Thank you. Good luck. Yeah.
Thank you, team 2. You can now stop presenting.
If you can still hear me.
And you can also lower your hands. The team members from team 10 who will be presenting, please raise your hand. We'll make you presenters. Team 2, you can stop sharing your screen. Screen is still being shared. Rohan, I think you are presenting your screen. Rohan, your screen is still being shared. Could you please stop presenting? Anyone else from IIT, from team 2, could you please tell your teammate to stop sharing their screen?
Hello?
Yeah, hi Shubham.
Yeah.
Yeah,
Hello. Hi.
Rohan is not sure what's happening with Teams because he doesn't even have presentation rights anymore.
No, I actually have made him a presenter again. So people from team 10, can you see Rohan's presentation on the screen?
We can see.
It's gone now.
Now it's gone.
Yeah, it's gone. All right. So team 10 is briefing you. At 13 minutes, we'll be ringing a bell. As you could see for the previous presentation, little indication that there are 2 minutes left in your presentation time. So you would have to wrap up in the next 2 minutes. All right. So team 10, you can start sharing your screen and you can tell us when you're ready. We'll start the time. And are there 4 people from your team who will be presenting, or will any more people be coming?
Now, the people presenting are here. Can you see my screen?
Yeah, we can see the screen.
Yes, please.
Okay, so we are starting now. Good. So we are Team 10 presenting a solution for BOSCH model extraction attack for video classification. So the basic methodology that we followed for the problem statement was we first trained a generator to generate the synthetic videos, and then we used the synthetic videos to get the labels from the victim model. And subsequently, we use those predictions or the labels to train the threat model so that it can imitate the victim model. And so moving on, we have, am I audible?
Yes, you are audible.
Okay, good. So the threat model that we have used for the problem statement is Vivid, also known as Video Vision Transformer. The features of Vivid are that it extracts spatial temporal tokens from the video and then feeds it to the input transformers. And it also factorizes the attention model into two sections: the spatial attention model and the temporal attention model, to fasten the training process. So the reason that we picked Vivid over other transformer or action classification model was its accuracy on kinetic 600 dataset, that is 93.8%. And the trainable parameters were also less, 4.045 billion parameters. And the main reason that we picked it was it can train effectively on smaller dataset because it effectively utilizes regularization into the training loop. So you can see the Vivid architecture here. As I mentioned, the attention block is factors into two sections: the spatial attention block and the temporal attention block. The spatial attention block focuses on getting the shapes and the geometric features of the videos right, and the temporal attention block focuses on getting the sequences and the temporal relation between the two frames, so that we can classify the action. The videos also are passed through a tokenizer first to generate embeddings, and these embeddings then are fed into the transformer block. These embeddings will play a major role after we explain the whole gray box and black box process. So moving on, we have the generator model.
Yes. So we have used Diagon as our generator. Yes, so this is the architecture of Diagon. There are two generators. One is for generating content weights, like we give inputs a random noise. We give two random vectors as the input to the generator. One is a content vector and another is motion vector. And as the name describes, content vector represents the content of the video, whereas the motion vector represents the transitions in the frames. So there are two generators corresponding to these two vectors, and they generate the corresponding weights. Then these weights are concatenated and passed through a video INR to generate the video. Similar to generator, there are two discriminators which are used to classify the video as real or fake. The content discriminator classifies the content of the video, whereas the motion discriminator classifies the motion of the video. So these are some of the salient features because of which we use Diagon over other video GANs. First of all, Diagon is faster both during training and inference. The major reason behind this is that Diagon uses the separation between motion and content. And another feature is the INRs. INRs are computationally less expensive, so that the training and inference both becomes faster. Now, what are INRs? INRs are basically some specialized neural networks which are used to represent images and videos as functions. So rather than representing videos as grids, videos as matrices, we represent them as functions of spatial coordinates x and y and temporal coordinates time. This allows them to theoretically have some infinite resolution. And since they are neural networks, they are not too much computationally expensive. Yes, next slide. So now coming to the gray box setting of the problem statement. So this is a methodology for solving it. First, we train again on the available 5% of the kinetics dataset. Then we generate videos from this trained generator and use the victim model to get their labels. Then once we have the synthetic dataset ready, we can train the threat model to imitate the victim model. Next slide. Yes, so this is the overall pipeline. We have a pre-trained Diagon which is trained on the 5% of kinetic dataset. We generate videos from it from random vectors. Then we can get the labels from the victim model. We can keep the data set ready before training the threat model. This reduces the number of queries. Then once we have the data set, we can train the threat model using the cross entropy loss and then backpropagate to train the model.
Okay, so now I'll be talking about the second part of the problem statement, that is the black box setting. Right? So one glaring issue when it comes to the black box setting is that we don't have any relevant data set to train on. Right? No relevant real world video or image data set that we can use. So to overcome this, we have implemented a data-free substitute training approach, right? Which basically involves a generator, which produces synthetic output from noise, which is used to train the threat model. Can we move on to the next slide, please? Yes. Okay. So the training pipeline is a little different from the gray box setting. Here we have a generator which is being trained in loop to produce videos from random noise. And once those samples are created, we use the victim model to obtain the labels of the victim model on these samples. And then the threat model is simply tasked to try to mimic the victim model on these samples that are currently being generated. The threat model training pipeline is quite similar to what we have seen a couple of slides back. The only difference is that we have a DIGAN here generating samples, and using the victim model, you can compute the output labels, and using the threat model, which is Vivid in our case, you can obtain the probability distribution. And using the simple cross entropy loss, you can backpropagate and train the threat model to try and mimic the victim model. But the issue here is that if during the course of training, you don't change the generator weight, you don't update the generator, then this is just equivalent to training on random noise. Why? Because the generator is not changing, it is not evolving to produce more and more relevant samples for the threat model to learn on. So the threat model will not gain any new information, right? And for that purpose, we also train the generator. And that's the generator training pipeline. So the forward pass is pretty much identical to what we have seen. But the thing is, we train the generator by imposing two loss functions. The first one is the diversity loss function, which enforces that the samples that the generator is creating are diverse enough, right? Because we want samples in most of the 400 or the 600 classes that we are working on, so that the threat model performs well. That's the first loss, right? And the second and the more interesting loss is the imitation loss. And it is exactly the opposite of what the threat model loss is. So whenever the generator feels that on the samples that it is currently producing, the threat model is able to mimic well the victim model, then the generator would update its weights in such a fashion that the samples that it would consequently produce are the ones on which the threat model will learn some new information. It is those will be the samples on which the threat model does not perform well, does not match the victim output. So this alternative fashion of training, because the generator is being trained in loop, so this alternative fashion of training can be viewed as a generator and threat model game, right? So when you're training the threat model, the task is pretty simple. You just have to learn to mimic the victim model for the samples that are currently being generated, right? And for the generation step, the generator has to learn to produce more and more relevant and diverse samples for the threat model to learn. And in theory, in theory, this game will converge. Why? Because this game is being indirectly supervised by the victim model, as we could see in the last slide. So as you can see, the imitation loss is a function of the query output label, right? So that means even though we are not backpropagating through the query output label, of course we cannot do that. We don't have access to the victim model weights, and we cannot backpropagate that. Even though that is the case, the query output label is driving the training of the generator, right? So that means the victim model is indirectly supervising the generator training, so that the generator evolves and learns to produce more and more relevant samples over each epoch. So moving forward.
So coming on to the generator analysis. Yeah, so these are some of the videos that are generated from the generator trained on 5% of Kinetics dataset. These videos could be understood in two parts. Their spatial and temporal features. Temporal features are related to the transition of the frames in the videos, whereas their spatial features are related to how the objects generated in the videos would appear to us. So as you can see, the videos produced are temporally consistent as the objects produced change through time without breaking and somewhat maintaining real world geometry. So coming on to the scores that we generated. So the accuracies of the extracted model on 1.5% of the Kinetics dataset are as follows. For the gray box setting, the accuracies are, for the Swinty model, it was 3.2%, whereas for the MovieNet, it was 1.23%. And for the black box setting, for the Swinty model, it was 1.6%, whereas for the MovieNet, it was nearly 1.2%. The state-of-the-art results of the black box approach is nearly 19.3% on the tiny image dataset, which is an image dataset, of course. The kinetics dataset is, on the other hand, is a much more complex video dataset with sufficiently large number of classes. And thus, the accuracy of the extracted black box model is comparatively low for the black box setting. Yeah. Coming on to the further improvements that we noticed. The first improvement is using conditional GANs. So GANs trained on complex dataset show a sign of mode collapse. Now, mode collapse is when the generator produces videos belonging to some class in the data distribution. This has resulted in decreasing the accuracy of both the black box and the gray box approach, as the videos generated by the generator are concentrated to some classes, and thus the extracted model could not learn on the remaining classes. Yeah. And what we propose is to use conditional training. In conditional training, the classes are also fed as a parameter to the generator, and thus a more diverse dataset could be produced, and the learning would be better for the black box as well, for the black box as well as the gray box approach. Coming on to the next improvement was the use of class-based encoders. We have used a single generator in the black box approach. Instead, what we propose is we could have declared different encoders for every class, which could have resulted in a more diverse dataset, as there would be different weights of the generator for different classes. The kinetics dataset had nearly 600 classes, and thus the model would become much more complex. This approach was not feasible to implement due to the available compute. And yeah, that's all. Thanks. That's all from our side. We are open to your questions.
Okay, I'll just switch on my video. Thanks for a wonderful presentation. Thanks for walking us through the approach. Very interesting. I just had a couple of questions. Can you go back 2-3 slides? You have quoted some black box SOTA matrix on tiny ImageNet. Yeah. Can you quote the source, please? Like where it's only 20% is quite striking. Basically, can you just quote the source or just help me understand what is this?
Sahil, will you take this on question? Sahil, you're muted.
Yes, so like when we were literature reviewing over various methods, then we came across this research paper known as delving into data effective substitute training for black box attack. So like it was quoted there, the accuracies on various attack models. So
okay. Got it. So for me to understand, you went to a paper which was telling you about how to do, let's say, video extraction, and they tried a black box matrix, and that was maybe SOTA on their perspective, which was 20%, right?
No, so that was on an image-based data set.
Exactly. So image-based only 20% is a black box SOTA is what that paper claimed, is it?
Yes, on image data. Yes.
Okay.
And these accuracies are on top 1 classes, of course. I mean, the state-of-the-art accuracy is on top 1 class.
Okay. You had a
I had a question on the VBNet. Where
sorry, your voice is cracking. Could you please repeat that?
I had a question on VBNet. Where exactly is that incorporated in your architecture?
Yeah, so Vivid is the threat model, right? So that means you have the victim model, that is the oracle, right, through which you are trying to attack, right? And the threat model is the one that will converge to the victim model, right? So the Vivid is a threat model, and once you train this Vivid, then you can use this train model to attack the victim model, or you can use it to make the same queries but at no cost.
Can you go back to your black box architecture?
Yes, please.
So this is your architecture, right?
Yes, this is the
Yes.
threat model training pipeline. So Vivid is the threat model.
And how do you get probability distribution from the vivid? It's
I'm sorry.
a DIGAN output directly.
Could you please repeat that? I couldn't get that.
You compare the probability distribution output of your vivid with that of the victim model.
Yes, yes. How do we do that?
Is that one-to-one comparable in terms of number of classes for class entropy loss calculation?
No, yes, that was an issue. So what we did was basically the victim model is producing just one label, right? That's a very big limitation because when you are, let us say, querying some video on some web API, it is just giving you one label. It is not giving you entire probability distribution. Right? So what we do is we take that one label that is produced as a hard label, right? And using that, we match the generated probability distribution to mimic that hard label. I hope that answers your question.
Partly.
I see. So
But
is
you
that
do not have the complete probability distribution of both your threat
Yes.
and victim model.
No, I have the complete probability distribution of the thread model because that is completely trainable, that is fully visible to us, that is being trained from our side.
Across all classes. Okay.
Yes. So I have the probability logit of each class,
Okay.
each of the 400 or the 600 classes. Right? And the label is just one class, right? So that would be a one-hot probability distribution.
Good. Thank you.
Thank you.
Thank you. I think that those were questions from our side. Thanks. Thanks for a presentation and all the best.
Thank you for having us.
Thank you.
Thank you, Team 10. You can now lower your hands and stop presenting your screen. Team 11, the members who will be presenting, please raise your hand. All right, so I think we have 4 people. Yeah, we have 5 people over here. All right, guys. So at 13 minutes, we'll be ringing a bell, which will be an indication that 2 minutes are left for your presentation timing, and you have to wrap up your presentation. And then we'll have the Q&A session. All right, so you can start sharing your screen and tell us when you're ready. Yes, the screen is visible. All right, so you can start now.
Screen it. Team 11, all of you are muted. Are you starting the presentation?
We are facing a little bit of technical difficulty. We'll be starting in a minute.
Yeah.
Thank you for waiting for that.
Am I audible?
Yes,
Okay, so there was some network issue, so I'll start now.
no problem.
Yeah.
Uh, Hello everyone, this is Team 11 presenting our solution to the problem statement BOSCH's model extraction attack for video classification. So let's begin. Here is a brief rundown of our presentation. So the first part is the problem statement. So here we'll briefly describe the problem statement and where we'll discuss the settings and the constraints of the problem statement. Then we will move on individually to the black box setting and the gray box setting and discuss the strategies and the models that we have employed in both the settings. Then we move on to the literature survey. So now, as the title of the problem statement highlights, attack. So to attack, we need models, and choosing a model requires extensive study. So we briefly present our study behind the attack in this literature survey section. So then we look at the final results that we have obtained through our work with various settings. And finally, in the future work section, we present a few methods that we could have tried out given more time. So now let's look at the problem statement. So this novel problem statement draws its motivation from the increased use of deep learning in the current scenario, where companies across the globe are efficiently integrating the deep learning architectures into their data pipelines. But with pros come some cons. The black box nature of these deep learning architecture makes it impossible to understand the mechanism behind their predictions, and this makes it highly vulnerable to attacks that exploit these hidden mechanisms. We hope that with our proposed solution, Bosch is able to safeguard its models from such attacks. Now, detailing further on the problem statement, we are given to attack two victim models. The first one being the Swin Tiny model for action classification that has been trained on the Kinetics 400 dataset, and the MovieNet A2 base model that has been trained on the Kinetics 600 dataset. Now, let's look at the problem settings and the constraints. The problem statement describes two types of settings for model extraction. The first one is the black box setting, and the second one is the gray box setting. First, we will talk about the constraints that were common to both the settings. So in both the settings, we did not have access to the victim model architecture, the output class probability, or the class names that was given by the model. So the question arises, now how are these two settings different from each other? The answer can be inferred from their names itself. In the black box setting, we were not allowed to use any relevant data set, but with the liberty of using synthetic or generated data set without using the kinetic series data. But in the gray box setting, we were allowed to use 5% of the original data set for querying the victim model. So this 5% is said to be the balanced representation of classes. Now this was all about the problem statement and the settings.
Next, let us see the approach taken by us in the black box setting. This is a snapshot of our journey to solve the problem of black box. We first try out some basic methods, followed by understanding why they didn't work out. We then develop a complex strategy that not only improves the results, but also introduces new challenges to us. We then propose a mechanism to solve this challenge and finally take a look at the results. Since we are not allowed to use any datasets related to Kinetec's real-world human action video dataset, we try out a basic strategy to generate queries for the models. We use psychedelic animations, and as you can see here, they are noisy design patterns. We use custom Python code to generate these animations and produce predictions using the victim model to create the attack dataset. We trained on this dataset and could not improve upon a subpar score. We speculate that models trained on these queries learn to predict noise primarily and are inapplicable for real-world action datasets, that they do not contain real-world objects and any information needed to predict on them. So what do we do now? We hypothesize that we need to add spatial features for the model to enhance their understanding. We propose stacking open source images that contain real-life objects. We take multiple image datasets and stack them together to generate a temporarily meaningless video with image features for the model to learn. You can see an example video here, which consists of stacking various images. We query them against the victim model to generate the dataset. The process of data generation improved the training result as the features were more meaningful. You can see them. But there was a small challenge here while the creation of dataset. We observed that the data generated through custom random stacking had high amount of imbalance. You can take a look at the variation of class sizes, and these are just the top 10 classes. Now, how do we go upon solving this? We enhance the class balance through image-styled video inferencing. We take a single image and stack it multiple times to create a static video. We use this as a query to generate the predictions. In this mechanism, we set a predefined limit on the number of videos per class that need to be created that minimizes the queries. 2. We verify if this prediction can be added to our dataset while meeting the set threshold. If this does not satisfy, we do not include this video and start searching on a different dataset to minimize the redundant query. We consider the threshold as a parameter in our data pipeline. This mechanism left us with a near balanced dataset and increased the number of unique IDs from 145 to 383. You can see an example of image stack video in the next slide. You can see the picture of the bird is tagged multiple times, and this is passed to the model as a video. Finally, let us look at the results we obtained. I just explained the data preparation strategy, which was extremely important for threat model that we'll explain later in order to learn. The numbers represent the top 5 accuracy on the test dataset that we benchmarked our score on. The results improvement can be attributed primarily to increase the number of iterations and this threshold hyperparameter tuning. Next, let us look at a section of gray box. We first use the obvious approach of using next step. We first use the obvious approach of using the 5% kinetics dataset and obtain exceptional results. We then perform class-wise error analysis in order to improve any enhancements, and finally take a look at the results. We sample a 5% balanced representation of kinetics dataset and use them as queries to the victim model. The queries and predictions are used to train the threat model. After training, we obtain accuracies that are pretty good when compared to black box results. We suspected that fewer data points can pose a problem, although we explore ways to enhance results by augmenting information to the model, as increasing the information can provide more signal to the threat models. So how do we improve? Any standard ML pipeline involves looking at model predictions. As said before, the models are black box networks that and need to understand the inner workings of these neural networks. So we perform class-wise error analysis to see where the model fails to perform. We see how many errors does our model produce across different classes, and we filter the class IDs for which the model produces a high number of errors according to a predefined set threshold. This threshold is again a hyperparameter for a pipeline that we tune along with other parameters. And finally, let us take a look at the results that we obtained in the gray box. So these numbers again represent here the top 5 accuracy.
Now, we would like to move on to the literature review. So, first, I'd like to go over the models that we had primarily tried on the black box and gray box setting. These models include an efficient D0 with an LSTM attached to it, the Facebook AI Research slow fast model followed by their slow only model, and the time transformer. But the final model that we had chosen for our attack was the temporal segmentation network. Before diving into the architecture of the temporal segmentation network, I'd like to talk about a few other topics that played a role in our approach. The first would be efficientnet. The efficientnet group of models is a convolutional neural network based on the inverted bottleneck residual block of MobileNet V2 architecture, in addition with the squeeze and excitation block. This was attached to the long short-term memory module or LSTM, which is an artificial recurrent neural network architecture that, unlike standard feed-forward neural networks, has feedback connections. The ResNet group of models, which are pretty well known, use residual blocks and skip connections to solve the problem of vanishing gradient in deep convolutional neural networks. This helps in capturing more complex features using a larger number of layers. That is, a deeper model can be trained on a dataset without overfitting on it. This is followed by the time transformer model, which is a convolution-free approach to video classification built exclusively on self-attention over space and time. It adapts the standard transformer architecture to video by enabling spatiotemporal feature learning directly from a sequence of frame-level patches. Now, I'd like to start with the temporal segmentation network. So, the temporal segmentation network is an improvement over the two-stream convolutional neural network approach. An obvious problem for the two-stream convolutional neural network approach is that in the current form, they're unable in modeling long-range temporal structure. This is mainly due to limited access to temporal context as they're designed to operate only on single frame, that is spatial network, or single stack of frames in a short snippet, that is temporal network. However, complex actions such as sports actions comprise of multiple stages spanning over a relatively long time. So in TSN, instead of working on single frames or frame stacks, temporal segment networks operate on a sequence of short snippets sparsely sampled over the entire video. Each snippet in this sequence will produce its own preliminary prediction of action classes. Then a max voting type algorithm is run over all these predictions to get the video level prediction. In the learning process, the loss values of the video level predictions rather than those of snippet level predictions were used in the two-stream context. These are optimized by iteratively updating the model parameters. Now let's move on to our training strategy. To prevent the model from overfitting on any data, we use various augmentations such as random resize crop, video mix-up, and flip. We also train the model with an Adam optimizer with a learning rate of 7 into 10 to the power minus 7, which was empirically obtained by learning rate tuning. We found that given the hardware we had and the time constraint, this was the learning rate that worked best for us. We also used a step LR learning rate scheduler, which decreased the learning rate by a factor gamma every 3000 iterations. We also set the max gradient normalization to a value of 40, which helps us in avoiding the problem of exploding gradient. Now let's move on to the augmentation that we had used. The first augmentation that we have used was random resize crop. In random resize crop, a crop of the frame is taken and the short edge is resized to 256. Next one is video mix-up. In video mix-up, the frames of two videos are superimposed on each other. It is a weighted combination of two different data samples. This is useful as a neural network as they are prone to memorizing corrupt labels. Then the third one will be flips, which is just as simple as it sounds. A few randomly selected frames from the videos were flipped. Now, I'd like to go over the summary of our final results. So here, all results have been reported on a separate 10% dataset of the 5% balanced dataset that were downloaded from the validation set of both Kinetics 400 and 600. This 10% test set was only used after the models had been trained, as even in the black box setting, we could not use any relevant data from the Kinetics dataset to select our model while we were training it. So, firstly, in the K400 dataset from which we have to extract the twin tiny model, our phase 2 score, that is the final score after 110 epochs on the black box setting, was 39.42% top 5 accuracy, followed by 77.50% top 5 accuracy for the gray box setting. In this, when we had run the twin tiny model on our very own validation set, that was the test set, we got a accuracy of top 5 accuracy of 90.8%. In the Kinetic 600 dataset, from which we had to extract the MovieNet A2 base model for video classification, we got a black box score of 34.51% top 5 accuracy, followed by 75.36% top 5 accuracy for the gray box setting. When we had run the MovieNet A2 base model on our very own test set, we got a score of 89.4% top 5 accuracy. So from this, we can from this we can conclude that even if we have a very small number of images, a very small percentage of the data set, we can face an attack from we can face an attack that could take all our work and model. The amount of compute power we needed was also very less. We only had access to one RTX 8000 GPU, whereas the original models were trained on 8 B100 GPUs. So this reduces the cost that is needed to train our model as well. So from our work, we can show that a direct and hazardous threat to deploy DL models exists in the world. Continuing with our work, we can see a few of the future approaches that we could have taken given we had enough time and resources. So due to the nature of our problem statement and the really high training time, we had limitations on the number of models we could have tried out while selecting our attack model. We showed you the slow only and the slow fast model. These models were performing very well in the black box as well as the gray box setting. But the only caveat they had was they took a lot of training time and we could not have approached this problem using them. We found that the TSN model took less training time and could have trained it for more epochs, which was giving us a benefit in our score. The next thing we could have tried was active learning, in which we would have adopted a cyclic approach to labeling our data. For generating the dataset, GANs could also have been used, which would have generated similar videos to the one which had already been queried with our target model, and then we could have passed them on to the attack model with the same label. This would essentially have reduced the number of queries that we needed. We could also have adopted a better dataset generation method, which would have given our model more temporal and spatial features to learn from. The model could also have been tuned better, which would have led to drastic improvement in training given our limited time and resources. We would also, so that brings us to an end to our presentation. We would like to thank Bosch for giving us such a unique opportunity to work on an innovative problem statement that helped us learn a lot. Thank you. That brings an end to our presentation. We would like to invite questions from the judges.
Yeah.
It's unmuted.
I had a question. So first of all, very good. I had a question on how did you go about with this stacking data sets approach? Like what was the design approach, design decision to choose stacking data sets? And I also had a doubt, if you go back to this, yeah, are these the same images, or are these coming from different frames? So x, t minus 1, t minus 2, t minus 3, and so on, or are these all the same x of t? So these two questions.
So
Yeah,
we use
so-
in this.
So these all these images are, so it's a static video. So every frame in this video are same. So t minus 1, t plus 1, all are the same images. So what we basically do is we try to search for all the different classes that are present in the Kinetics 400 dataset. So we found that this approach gives us a greater chance of achieving getting all the classes of the Kinetics 400 and 600 dataset into our attack dataset.
Okay. But no specific reason how this would affect the model architecture, what exactly will it activate, and so on, from a maybe a self-attention based transformer point of view.
When we use randomly generated noisy animations that we just showed you, like psychedelic animations, we realize that models trained on these datasets cannot learn to predict on real-life objects like kinetics that we have. Hence, they can't effectively extract the model that is in the server. Hence, we need to add a slight spatial information in order for the model to learn. And without any relevant datasets, we propose this stacking method, which can add small amount of spatial information, but at the same time cannot have any temporal information.
All right, thank you.
Yeah. Yeah, Amit here. So thanks, team. First of all, very novel approach to this problem, and I think really good results as well. So firstly, congrats on that. So I just had one question, right? So now that you have attained, let's say, around 77% model accuracy against the original model accuracy of about 90%, right? So how do you, let's say, if you were given, let's say, more compute, or let's say, more resources, how do you think this query to, you achieving 90% correlation would be? Like, do you think in order to reach 90, let's say, like even higher accuracies, how do you think this would progress? Like, would you need more queries, more data sets, more compute power? Just help me understand how you think this will evolve.
So as we had mentioned before, we had tried out the pi slow fast model. So what we were observing in the slow fast model was that by training it just for about 5 epochs, we achieved a score that in our setting for the TSN, we achieved after 25 epochs. But the thing about the slow fast model was that because it is a two pathway method, that is the slow method and the fast method, where there's a difference in FPS and it does not use any static frames. So it was taking us 4.5 hours to train per epoch. So given we had more resources and more time, we would really try to pursue that approach, and we would and I would assume we would get much better results on this, because the scores that we have showed you were obtained after 110 epochs by training on the TSN. So if we had resources, we would have tried to train the slow fast model for about 110 or 150 epochs. So that would have given us much better results.
Okay, understood.
Yeah. Team, really good results, and I really like your approach. The question I have is more even bigger forward-looking question. How generalizable is your strategy? Let's say today you knew that you are using the action recognition and all of this thing. Tomorrow I give you a different kind of video classification task. How transferable is your approach?
So in our approach, we can see that we use images from a random number of data sets. Like we saw human faces dataset, Indian actors dataset. So from here we can see that even if we use a general purpose dataset, we can get a decent amount of accuracy on like action recognition dataset. And this approach should work on any other kind of video classification. But Kinetics as a whole is a very general purpose dataset. It takes a random number of videos from the YouTube website, and we get our scores on it, like get our predictions on it. So I'd say our method would be very generalizable on any kind of data set, as we do not really train anything that's specific to the Kinetics data set.
Understood. And what was your results on the MovieNet A2's extraction? Because I didn't see that in your entire presentation.
Yeah, like we showed it in the summary. I'll go over it again.
Yes.
So in the on the K600 dataset from which we had to extract the MovieNet A2 base module. In the black box setting, we got a top 5 accuracy of 34.51% using the TSN model. And in the gray box setting, we got a top 5 accuracy of 75.36% in the on the yeah, and this benchmark was about 89.4%. So we are pretty close, but it's not close.
Yeah, understood. So now the question that comes here is that at least in these two settings, your approach has remained common. Can I conclude that?
Yeah.
Okay. And then what was the difference? That why the number of queries have changed? Because if the approach has remained pretty much same, why do I see order of magnitude at least twice the query, or at least 1.78 the queries?
The way we approached the problem was that we first approached the gray box problem, right? So what we did was as the gray box problem is a much simpler task than a black box problem, so we did that first, and on that we could have validated our models with the 5% the separate test set that we have created. So we got the best model from that, and as the Kinetic 600 data set is a much bigger data set than the Kinetic 400 data set. So 5% of a much bigger data set would be bigger, right? So that's why we had about 45,000 queries for the Kinetic 600 data set, which is 5% from the Kinetic 600 data set, which was augmented with our generated data that we had generated for the black box task. So that's why the number of queries between the two is larger. But the data sets are larger originally.
Understood. Yes, go on, please.
Judges, please wrap up the session as the 5 minutes for the allotted question and is over.
Okay. Thanks, Varshita. I think that's all from our side. Good luck, team. It was a great work.
Thank you, sir.
Thank you, Team 11, for your presentation. You can lower your hands and stop presenting the screen. Team 6, the ones who will be presenting can raise their hands. I can see 6 hands raised. A maximum of 5 people can present. And also, like among those 5 people, only the Q&A section has to be answered. So.
Hello, I think Shreya Shajal is not in our. She's not supposed to raise her hand. She's not in our contingent.
Okay, cool.
Yeah.
Yeah, so you can present your screen.
Yeah, 1 second. Yeah, I hope you can see my screen.
Yeah, we can see your screen. Tell us when you're ready and we'll start the time.
Yeah. We're ready? Yeah.
Yep.
We'll probably start.
Okay, good to go. All right. Good morning, everyone. We're Team 6, and we're here to present our approach for the BOSCH model extraction challenge for video classification. So we could move on to the next slide, please. Yeah. So we will not bore you with the details of the PS again, since it has been iterated quite a few times already. But what I would like to do instead is go over some of the key challenges that we faced, which largely motivated our choice of models and the training mechanisms that we adopted to get the results that we have. Right? So there are three aspects to this. One is related to the task itself. Right? So action recognition as it's on its own is quite a complex task. And the fact that we are dealing with a data set that has a large number of classes makes it even more difficult. Right? Secondly, about the modeling itself, there's not much literature which really discusses model extraction for models that deal with video classification. What that means is we did not really have a model that we could use as a head start and basically fine tune that or use some other tweaks in order to improve the performance based on that. Right? So whatever we built, it was the ideas were built from scratch. The third point is related to the data set itself, right? And we all know that the scale of data sets that we're working here with is quite large. That imposes two problems really. One is related to the logistics about storing and moving it around, and secondly, even training on them or validating on them takes a lot of time. With regards to the black box track particularly, from our understanding of the problem statement, we were under the impression that we have absolutely no access to any data set out there. And what that means is we'll be forced to generate some fake samples using models such as VideoGAN. But then again, even in that, there is a problem in the fact that there is a lack of good quality VideoGAN generators out there, especially for the classes that we are dealing with. So there's no class condition VideoGANs out there which really generate good quality samples. So we did not really have the option of using that either. Right, so having mentioned these two problems and the challenges that we face, let's move on with the approach. And I would like to introduce the black box track here. So the overall setting in this track is that we have a victim model, which we call the teacher model in our setup. And what we do is we use a GAN that we have fine-tuned in order to get highly confident samples out of the teacher model. And then using these highly confident predictions from the teacher model, we train an auxiliary model, which we call the student model, to mimic the teacher model, right? So which basically does the attack or extracts the performance of the teacher model. And this process is commonly known as knowledge distillation. And yeah, so that is the overall setup of this problem. I will now like to hand it over to my colleague who will go into the details of how we trained it and the models we chose, and we can take it forward.
Yeah. So the first step, as mentioned before, for black box generation is to generate synthetic data. So like as mentioned before, there were no particular class condition video GANs which generated very high quality samples. So our main approach was to repurpose a pre-trained big GAN, which is trained on ImageNet, to generate fake samples. The way we did this is a big GAN basically samples two input vectors. It basically samples a random latent vector as well as a class conditioned latent vector, class conditioned embedding. So what we did was we basically tried to learn embeddings for each class index predicted by the teacher. So therefore, we are not trying to have any prior information regarding what the classes are or what the data set itself is. So basically, we freeze the generator and the teacher model and fine-tune to minimize the loss between the teacher and predicted class index and the sample class index. We fine-tune this model for a few steps until the predicted class confidence for the given class embedding is greater than 90%. To again reiterate it in a diagrammatic manner. So we have a class embedding which is trainable. So these class embeddings are basically sampled based on the big GAN's pre-trained ImageNet class embeddings. And basically we sample a 0.1 radius Gaussian ball around it and set when we initialize our embeddings this way so that it has some sort of idea based on its pre-training information. And then we basically sample a latent vector, which is then passed on to a pre-trained GAN. Again, the pre-trained GAN is fixed. We do not train the GAN's parameters. We only train the class embeddings. And then this generated image is then passed on to a teacher, which is again frozen. We do not have access to it. And then based on the predicted class, we apply a loss to ensure that the randomly sampled class index is the same as the predicted class. So this is our overall approach. Now we go ahead and show some of our synthetic samples. Considering that the above approach is not very straightforward, we decided to sort of visualize these synthetic samples and then try to correlate with our classes which we have in hand to make sense if the generated samples are very meaningful or not. So for example, the image on the left corresponds to samples which are generated for class index 1 or air drumming class. Please note that we do not require this prior information of what the class itself is, but it's just for the sake of visualizing our results and interpreting our model that we try to show this here. So for this particular, although the images are not very visually appealing, we can see that they sort of resemble drums or frying pans, like some flat surface on which you can beat. And they are able to fool the teacher classifier with extremely high confidence. For example, so the way we have trained the class embeddings is such that the class confidence predicted is greater than 90%. Thus, the generated samples belong to the exact training distribution of the teacher network, which is the most essential part of knowledge distillation. Here is another synthetic sample. We can see that for class index 0, which is app ceiling, these are the synthetic images generated. So yeah, we can now move to the next part of the presentation.
So having gone over the data generation part, now I'll cover the architecture and approach we use for knowledge distillation. So the MovieNet backbone, a student model had a CNN backbone. So we went ahead with a ResNet 50 teacher. And since the Swinty backbone had a transformer-based backbone, we went ahead with VIT Tiny, which also had a transformer backbone. We had experimented with using ResNet 50 also as a backbone for Swinty, but the results we got with VIT Tiny were better. So now you guys might be wondering that how could we use an image-based models for video classification? So what we did was the samples we generated from Big GAN were concatenated to form videos, and then these were and the student models classified them frame by frame to get the feature vectors for each of the frames. Then we used average pooling across the frames to finally generate a feature vector representing the entire video that was further used for classification. And now moving on to the next slide, I'll explain our approach we use for knowledge distillation. So the videos that were generated using the concatenation of the generated frames were passed to the teacher models whose weights were frozen, and we obtained the logits for it. The same videos were passed to our student model, VIT Tiny or ResNet 50, and the logits were generated from the student models as well. Then we used a weighted combination of KL loss and cross entropy loss to minimize the distance between these two logit distributions, and used an Adam optimizer to train the student model to generate the mimic the logits of the teacher distribution. Now moving on to the next slide, we present our scores that we got for black box model extraction. So for video swing transformer, for which we use VIT Tiny, we got a top 5 accuracy of 7.8%, which is approximately 3000 times better than the random baseline. And similarly for MovieNet, we got an accuracy of 12.43%, which is 7000 times better than the random baseline. So given that these models were trained entirely on synthetically generated data with no access to any open source data sets, we believe that these scores are pretty good, assuming we also had very little time and resources to fine tune our losses.
So next up, we have the gray box approach. So unlike the black box setting, the gray box setting allows us to make use of auxiliary data sets. And other than this, the setting is pretty much the same. We have a fixed teacher model and a trainable student model. So we adopt a similar approach as our black box setting, starting with the knowledge distillation, where we use the auxiliary data, and followed by fine-tuning using the 5% kinetic strain split. So can we move on to the next slide? Yeah, so for the distillation, as previously justified, we use a VIT Tiny for the swing transformer and a ResNet 50 for the MovieNet. The only difference being that we use videos sampled from the auxiliary dataset to query the frozen teacher model in place of the synthetically generated frames. So the main thing is the choice of the auxiliary dataset was made keeping in mind that there should be very minimal overlap between the auxiliary dataset and the kinetics dataset. So we ended up using the moments in time dataset, which comprises of 305 classes, which covers a spectrum of actions that were performed by humans, unlike other datasets that were available like AVID or some specific class Q datasets like the sports datasets and so on. So now coming to the large size of the dataset. So we decided to perform all our distillation using only 4% of the auxiliary dataset. So if you see the number of queries for that, it was around 31,000 queries for the gray box. Now we finally fine-tune our student model using the kinetics dataset, the 5% train split, in a very novel manner.
After the step of knowledge distillation, we had to our disposal 5% of the kinetics dataset, which we want to use to fine-tune our model. Now, because this is a relatively small size of actual training data, we want to induce some sparsity in our model, which acts as a regularization to avoid overfitting. And also we want to induce some inductive bias specific to this data set. For this, we use the lottery ticket hypothesis. This hypothesis states that there exists a subnetwork within any network that can do as good as or better than your current performing network, and you will also obtain a sparse network. This network is called a winning ticket. So to find this winning ticket, we do the following procedure. We first train our knowledge distilled model on the 5% data set for a few iterations. Then we mask out some of the weights based on the magnitude, and we reinitialize them and repeat this process again and again till we obtain the winning ticket. Now we will see that the winning ticket gives us a very big improvement in the scores. Okay, so these are the scores that we've obtained through fine tuning. Now, on doing just noise distillation, we get 8.3% on VideoSwin and 13.8% on MovieNet. We see that they are slightly better than the black box scores because we have been using actual data set compared to the synthetically generated data set. After this, if we just fine tune after knowledge distillation, we get a score of 12.6% and 22.3%. These are all top 5 accuracies. Now, after, instead of fine tuning, if we decide to go with the lottery ticket hypothesis approach, we see that we get a considerable bump in score, which is 17.3% on the VideoSwin transformer and 33.5% on the MovieNet. And these are the winning tickets that we found through the lottery ticket hypothesis. So this is the end of our presentation. We would like to thank the BOSCH team for putting forward this PS. It was quite challenging and we had a fun journey learning through. Thank you for your time.
Hi team, so good job. First of all, why have you gone with knowledge distillation 1, and what is the ratio in terms of model parameters? Original model is to student model. What is the ratio in terms of model size?
What did you mean by knowledge distillation 1? Like, I didn't.
I mean, you've used knowledge distillation as one of the steps, right? So
Right.
So I would like to understand the ratio of model size, the teacher model versus the student model. What's the ratio there?
So our VIT based models are roughly around VIT Tiny is roughly around 2 million parameters, if I'm not wrong, which is our student model for the video swim transformer task. And for MovieNet, we use ResNet 50. ResNet 50 is around 33 million parameters, if I'm not wrong. And the original MovieNet Con 3D sizes are much larger. I'm not sure about the exact number, but they are definitely much smaller than the teacher models for sure.
Okay. The follow-up question: would you attribute the accuracy here that you have with MovieNet to ResNet, or why do you think that you have this increased accuracy for MovieNet when compared to
Right. So the thing is, as all of you know from most of these popular papers from transformers, that transformers are very difficult to train as they completely lack inductive biases. So when you have a very small data set or very few number of samples, it's very, very difficult to train the model from scratch. Whereas ResNets are not that way. They always have a very good base performance irrespective of the data set size. And they have completely good, very strong inductive biases because of the way convolutions work. So that is entirely the reason why we get improved performance in MovieNet rather than the video swim transformer.
Okay. And going back to the question, let's say if you have the synthetic GAN generation, how do you think we can use this going ahead to improve your accuracy? If you have to only look at improving, what would you do to improve? Would you look at only the synthetic data generation or what else?
So first thing is that, yes, we would obviously like to improve the synthetic data generation, because you can see that although the images are able to fool the teacher network, they are not particularly visually appealing. So beyond a sense, we cannot expect it to sort of mimic a completely real data set. So improving this is something which is very important, because we had very limited compute and time. So we had only trained for each class index, we had only fine-tuned for like 100 steps or so. So it was like a very quick training to generate these images. And because of the way we are training it, and only since you're having the class embedding trainable, we were able to get these good results. So one thing is obviously to improve the synthetic data generation. And then beyond that, I guess we could try to look at better knowledge distillation approaches. There are some recent methods which try to do it slightly better. But I would basically say that we would mainly want to improve the synthetic data generation. That's something which we need to mainly focus on. And if there was a video GAN, like for example, over here, we have used a pre-trained big GAN which generates images. But for our task, we actually need a video generator. So if there was a very powerful class conditionable video GAN, that would be something which we could better fine tune rather than using a pre-trained big GAN. So those are some requirements. If we could achieve better performance.
All right, thank you.
No. Is that all, or are there any?
Yeah, I think these are all from our side. Thanks.
Yeah, thank you.
Thank you.
Okay, team 6, you can lower down your hands, and team 17 members, please raise your hand. Team 17, you can unmute your mics and start your presentation. Tell me when you're ready.
Just give him some moment.
Yeah, it's fine.
Hopefully, my screen is visible and I'm perfectly audible.
Yes, you
it's
are.
visible and you're audible.
So, greetings judges, this is Team 17 and we would like to present our solution for the BOSCH model extraction attack for video classification. So just to give you a brief insight, what we understood of model extraction was that it is a kind of attack in which the adversary aims to replicate the model, the performance of the victim model, and essentially steal its capabilities by performing the minimum number of queries and with minimal access to the victim. And this problem statement tasks us with devising strategies for under two settings, black box and gray box, for two of the victim models. So first, I would like to lay down our core assumptions, which we use to build a solution. Firstly, in both the black box and the gray box settings, we assumed that we had no access to the architecture of the model whatsoever. All we had access were the class labels, which are predicted by the model on sending it an input in the form of a video. Also, with respect to the data set on which these victim models were trained, we did not assume to have any information on them, apart from the fact that what were the number of classes within each of these data sets. That is 600 in kinetics 600 and 400 in kinetics 400. And for the gray box setting, we assumed that the data set was well known in advance, though we did not use this information. Our solution essentially is capable of performing without this information. So first, I would like to start off with explaining our methodology under the black box setting. So this is our flow diagram of our solution. Let's start off with, we first take up a random noise vector from a latent space and pass it to a generator model. Now the generator model used here is a 3D generator, which produces images. Now to convert this to a video, we basically stack all these images across the temporal dimensions, or basically repeat them. Now, the main cause of us doing this is because in the literature, it has been well proven that most of the information of the video is constrained in a single frame and is sufficient to generate reasonable inferences. And thus, we use a 3D generator model. Now, after repeating it across temporal dimensions as in the form of a video input, we pass it to a victim model and the surrogate model, which here is the extracted model in this case. For the surrogate model, we have used 4D ResNet, which I'll be elaborating on in a short while. So from the victim model, we obtain the class labels, and from the surrogate model, we get the probabilities across each of the classes. Then we use a cross entropy loss to calculate the loss values. And now the basic, the most important part of the approach comes here. Now, given the fact that the generator and the surrogate have to be trained in a parallel fashion, so simultaneously, we use the same loss function to train both the generator and the surrogate. But the core difference lies in the very fact that the surrogate model is trained on minimizing the loss function, whereas generator model is trained on maximizing the loss function. The reason why is because we want the surrogate model to predict as close as the victim model, whereas the main core of the generator is to generate videos which try to increase the diversity and make the surrogate model misclassify. So it's the same loss function, but opposing, it's used in the opposing nature. Also, as for the generator, if we for the purpose of backpropagation, we do not know the architecture of the victim model, so we use the method of forward differences to approximate the gradients across it. So as I stated, we use the we use a 3D generator and just repeated it across the temporal dimensions. And yet, I would also like to say that it also led to a reduce in computation cost as compared to using a 4D generator for a purpose. Here are experimental settings. For the generator, we use a 3D GAN. For the surrogate model, we used a 4D resident, that is the R2+1T. Now, the very advantages of this architecture are twofold. Firstly, it tries to approximate the very function of 3D convolutions by breaking it down into 2D convolutions and 1D convolutions stacked together. This ensures that the optimization process is easier and much more efficient. And at the same time, it increases the number of nonlinearities in the network, so it allows us to learn. We used 500 iterations, not very much, but it was only possible from us given the scarce computing resources we had. And we used well-defined strategies such as using learning rate schedulers to decrease the learning rate over time. For the optimizer, we used the stochastic gradient descent for the generator and Adam for the surrogate. Reason being, SJD generalizes better than Adam, even though it requires a higher it requires higher training steps, whereas Adam basically converges faster. So we want our optimizer to generate images in a variable fashion. So our choice of optimizer was defined as such. So for the purpose of evaluation, we took 50% of the validation split of each of the data sets while ensuring each of the classes were equally represented within that data set. And we also benchmarked the victim models on a validation split in order to get a better insight how our stacked or surrogate models were performing. So these were the metrics obtained by us. For the MovieNet model, we obtained a subpar accuracy. So we believe that this could be the very nature of the validation split we took. That is why we had such poor accuracy even on the victim model itself. And the extracted model or the surrogate model had representable accuracies. So to mention about the challenges we faced, firstly was the lack of computing resources, due to which you cannot train. We firmly believe that if we had considerable time and computing resources, we would have trained our models to an even larger iterations. And that would have led to an increase in the accuracy, because what we observed during the training process that it was stable and the loss was continuously on the decrease. Also, given the fact that kinetic data sets were quite large, so downloading them was a challenge. Another thing what we saw in our training process was the problem of mode collapse, wherein our video generator was producing the same image, same video predictions from the victim over and over. What I mean by this is that while the videos had inherent differences between them, but our victim model were classifying them as according to them the same class label. So this was a problem, and we felt that using conditional GAN might solve this issue because conditional GAN uses an additional constraint of the classes in order to generate the videos. So that might be a solution to this issue, but we lack the resources to train. Now we'll be discussing Greybox, and I would like to pass on to my next team.
Hello, good morning everyone. We will now discuss the approach we used in gray box setting. Similar to the black box setting, we were unaware of the model architecture in this setting. However, here the dataset that was used to train the model, the victim model, was well known in advance. For both the victim models, we used a video generator that was pre-trained on the UCF101 dataset that produced a random 4D video tensor, which is used as inputs to both the models. For the choice of surrogate model, we have employed slightly different strategies. It is extensively discussed in the literature that most of the significant information of a video is present in the frames in between, and that can be used for the classification. Furthermore, it is computationally very budget-friendly to use a 3D architecture instead of 4D. Hence, for the P1 problem statement, we have used the ResNet model that takes in 3D frames as an input and protects the corresponding classes. Kindly note that here we are passing the same video generated by the generator to the gray box model. For the problem statement P2, we have passed the video as it is to our surrogate model as input, and we predict out the classes. These two approaches were taken in parallel for efficient utilization of our time. We wanted to study both the architecture setups and wanted to choose that the one which provided us with better results. For the first architecture in the figure A, we take only the middle frames and we pass it to our surrogate model, whereas the whole video is passed to the victim model, by which we get our class labels. The surrogate model provides us the logics, and using the class labels and logics, we apply a cross-entropy loss function and backpropagate to update our weights. Compared to the movie test victim, both the victim model and surrogate model are being passed the same input, and we get the class labels and logics respectively, which are passed to the loss function, and the backpropagation happens. Can we the next slide, please? Next slide. In experimental settings, as we mentioned that for both the victims, we are using video generator trained on the UCF101 dataset. Kindly noted, since we are utilizing a 3D architecture for the SwimT victim, we have used only 1/3 of the video frames for the generated video for the training. However, during the inference, we have used the middle frame for the prediction. As opposed, for the MovieNet victim, we have used the generated video for the training the 4D surrogate model, but during the inference, we use only 16 frames of the generated video due to computational constraints. We have used learning rate schedulers for each of the models to gradually decrease the LR over the iteration. Finally, we use the cross-entropy loss for both the victims. Next slide. Similar to the black box setting, we have taken the 50% of the validation dataset for reporting our results. Kindly note that we ensure a balanced class representation here also. Moreover, to better understand the efficacy of our model, we have benchmarked the victim models. The results are reported in this slide. We obtain a top 5 accuracy of 1.29% for our P1 victim with a total of 43,200 queries made. For the kinetics 600 dataset, that is for P2's problem statement, obtain 0.83% accuracy with the queries of 3,200. Kindly note that we did not observe any significant performance gains on the increasing number of queries in the P2 setting, and we went ahead with this setting only. Moving on to the challenges. Again, the same challenges we were facing in the black box setting were faced in this setting as well. We were affected by the lack of adequate computing resources. It prevented us from training our model to its full potential. Further, please note that in order to run the evaluation script on Google Colab, we limited the number of frames per video to 32 and 16 respectively for Swinty and MovieNet models. In conclusion, we found the problem statement to be practical and novel. The system works on the extraction attacks are limited to image classification models only. In video-based models, there is an additional temporal component that provides an inherent defense to these models, which in turn makes it difficult to mimic these models. Moreover, the earlier extraction attacks or extraction strategies contained a very small number of classes as compared to the number of classes for the given problem statement, which is 400 and 600 respectively. Due to these lack of these aspects in literature, we had to employ a detailed study for the approach in order to build an efficient architecture. We believe that given adequate computational resources and time, we would have obtained substantially better results for these problem statements. At the end, we would sincerely want to thank the BOSCH team for this novel and practical problem statement. Thank you.
Thank you, team, for this wonderful presentation as well as the approach that you have taken. I hope that am I audible?
Yes, sir.
Okay, good. Thanks. Couple of questions, and especially this are on to the black box. Can you go back to your black box results slide, please? Yes, please. Here. I have a question that the top 5 victim models accuracy which has been reported on the Kinetics 400 and Kinetics 600. Was that the accuracy that you have generated, or was that the accuracy of the SOTA model where the link is given?
Actually, sir, we used the SOTA model on which the link was given, and we evaluated on our script, which was written to query the data sets, both Kinetics 400 and 600, especially its more specifically its validation splits.
Understood.
So the models were.
And just one more question there is that, have you used the all validation data set to report this accuracy?
50% of the validation set. In Kinetics 400, there were 20,000 examples. So we used around 10,000 of them for the purpose of evaluation. And for the Kinetics 600, there were around 30,000 examples in the validation set, and we used 50,000 to report our metrics.
Are you sure that your results are consistent? Because I have a fundamental question there, that your baseline, that what you are reporting, the baseline what you are reporting is substantially lower than anything else.
I mean, sir, we use the same state-of-the-art models for which the links were given. We performed no modifications on them. And I mean, we can, from our side, we can pin this cost to the split of the data set taken. But and also, yes, there could be another reason for this, because on Google Collaboratory, it did not allow us to pass the whole video to the machine learning, to the victim model as such. So we had to limit the number of frames, which we mentioned in a slide as 16 for Swinty and 32 frames for MovieNet.
Understood. So in this cases, what I understand is that the model remained the same, but the data which you have sampled, you are not able to pass through the complete data, and therefore your victim model's baseline accuracy is low. Is that an accurate statement?
Yes, sir. That could be an accurate statement.
Okay. Okay. Yeah, because that was the biggest question that we had there in terms of this. Now, can you go back to the gray box? Can you just stay on to the experimental settings, please? Yes. I have a question, especially on the optimizers. What was the reason of choosing two different optimizers, one for the SGD and one for the ADAM? Was it an informed decision? And if yes, what was the reason?
So for this R2 plus 1D resonance, this is a 4D model, 4D architecture, and we found that using an atom optimizer, this was so basically our due to our experiments, like we ran on atom and SGD as well. So we found that atom was performing better for the 4D architecture, and as opposed to the 3D one, we found that SGD is was giving the better results. The training metrics which we were reporting were better in case of SGD.
Understood. And how much you are sure that the results were only because of the optimizer and not because of your data, the way that you have constructed your data?
So essentially, we were using the same set of data, like the generated videos were originally sampled with us, and after that, once the data was generated, we were using that data only for the training. So the data was consistent.
So if the data was consistent, then the optimizer choices were informed by based upon the architecture, or it was just the empirical choice that you did it based upon some small experimentation. What I am asking is what is the experimental decision, or was it a theoretical backing for that?
Sir, we can attribute it partly to experimental observations. But yes, one thing we can say for sure from a theoretical perspective is that for 4D model, it was necessitated that we use Adam because SJD converges a lot more slower as compared to Adam. So we had to use Adam for 4D results.
Yeah, because then my counter question would have been that the Adam was the optimal choice for both of the case. Why in the first case you use the SGD?
Because SJD features better generalization performance over Adam, sir. And as the computational resources were quite less, comparatively less for 3D models, we could have trained it to even larger iterations, and then it would have eventually surpassed Adam.
Understood. Perfect. Now, can you go to the results? And this would be my last question before I give it to my colleagues. Yep. Can you tell me why the queries for the Kinetic 600 were only 3,200, where the Kinetics 4000 you had the 43,200 queries? I'm still failing to understand the result, understand this interpretation of this queries made here.
Yes, sir, I'll explain this. So the reason being, as explained by my colleague here, is that we trained both of these models in parallel. And what we observed was that during the training itself, we did not achieve a major decrease in the metrics in respect to the P2 model, which in which the movie net was the victim. So we stopped the training midway with the intention that we would actually replicate our P1 strategy for the P2 model, but apparently we weren't able to do that given the time constraint.
Okay. Thank you for your answers.
I have a question regarding the video GAN that you've used for gray box setting. Do you think if you had used any other synthetic or similar gray box setting, do you think you would have had better gray box accuracy? Because the tendency that you see is typically in a gray box setting, we would see very high or at least comparatively better results as compared to black box setting, but the results are the same. We don't see an improvement at all. And there the question is, has the video generator or the video GAN failed there?
So we would like to state that the video GAN was performing perfectly fine because during the training process, we observed the predictions of the victim model that it was giving on the data set, and we observed that the predictions of that victim model were varied on our data sets. It did not follow a certain pattern or approach. So as we only need the class probabilities, and as long as we are getting a variation in the victim model, I think the issue lies not with the video generator, but rather it was a mere case of undertraining.
Okay, because I see exactly to the decimal point that the top 5 accuracies of black box and gray box are the same. So I'm wondering how the 5% data that we have gotten in gray box, have we leveraged that? And from the data,
so we
it doesn't seem so.
so five. Yes, so for the 5% data, we basically did not use it in entirety, but rather we just noticed attributes, and using that data, we actually reached to a conclusion that we should use this video GAN for generating videos trained on the UCF01 dataset. So that 5% dataset was merely used for making a choice for which generator we had to use. But we did not use that 5% dataset at any point in the training. It was just used to make the decisions on what would be the choice of a generator.
All right. Yeah.
All right. Thanks, team. Good luck.
Thank you, everyone.
Thank you.
Yeah, thank you, team 17. Please just lower your hands. And team 1, please raise your hands. Team 1, please raise your hands. All the members of team 1, please, is there anyone present? Please raise your hands.
So we are not exactly sure what's happening with team 1, whether they're not present in the meeting. I've also sent a message to them. Be responding. So we'll proceed with the next team. If there are members of team 5 in the meeting, could you please raise your hand? Okay, I guess. Judges, please give us a few minutes. I'm going to contact them. Call.
Okay.
Team 1 members are trying to join. They're having some issues. They're trying to join through incognito mode. If it doesn't work out within the next 2 minutes, then we'll continue with team guys. Steve Bhimani, I think you're from Team 1. Could you please raise your hand? The members I can see from Team 1 are Shreyas Chatterjee, Steve Bhimani, Ajit Kumar Verma, Ashutosh Gangwar,
Oh
Kshitij
my
Gera,
God.
Mohit.
Thank God. दुख रहा था यार मेरा.
If any of the names that I just took is present in the meeting, please raise your hand. Keith, I can see that you're there in the meeting.
Yes.
Yeah, Keith, could you please unmute and like tell us the status of
Yes, ma'am.
your meeting?
Can you also take my members in, like so they can also speak?
Could you tell them to raise their hands? Like, there's nothing like taking in. Like, everybody would be able to join the meeting.
I don't know. They might not know how to raise hand or something.
So you get a reactions option at the top. You see people, chat, reactions. You click on reactions and then you find the raise hand feature. You'll see a hand.
Would you please give me a moment? Then I can call them and just let them know.
Yeah, yeah, sure. Please call them as early.
Yes.
Okay, so team one members, could you please raise your hand? We'll make you present. Steve, could you please tell your team members to raise their hand?
Yes, I have told them, and yes, they'll be doing it.
How long is it going to take?
Yes, they'll just do it.
Team one, are you going to present? Is anybody from the team going to raise their hands or we'll move to the next?
Ma'am, I'm sharing my screen.
So are there only two people from your team who are going to present? I can see team one event captain and see you are also there. So it's just the two of you?
Sorry?
Is it just the two of you? Like I can see you and I can also see somebody named team one event captain. So is it going to be just the two of you?
Yes, currently I guess
Yes.
only two of us have joined.
Since the others are not being able to join, Tirth will go ahead with the presentation.
Yes.
Sure. You can
So,
start.
okay. Good morning. My name is Tirth Pramani, and my team members are Shreyas Chatterjee, Ajit sir, and Kshitij and Asutosh. And we have done uh, we have participated in BOSCH model extraction. So first, as we had a problem statement, first we have gone through internet and try to understand what is the problem statement and what we have to do exactly to solve the problem. So at first it was very confusing for us that in first page of problem statement it was given that you in big companies there are many AI models, and there is also danger on AI models that if someone attacks on AI model, then that might leak data of companies which can be sensitive data. So the company also need to protect the data of AI models also. But on the second page, there was given two research paper of action video classification. There, uh, at that point, we were not able to connect problem statement, like what we need to do. In first page, it was given that we need to secure our AI models, and in second page, it was given about video classification. So we have gone through internet and we tried to understand what we have to do. So at first we need to understand what are terminology of gray box and black box. For that we have read a research paper and we got to know that gray box is a terminology. Gray box and black box is a terminology is hacker use when they want to know about AI model deployed in any website. And by gray box and black box query, a hacker can have access to model of company that they have made, and they can replicate that model, and with after replication they can provide that service at less cost, or they can also leak some data of company. So that is a sensitive thing. After that we tried to at first we tried solving with gray box, and gray box we have extracted the kinetics 600 data set. And but at first we tried to make a model on our own, but at first it uh, we have made a base model, but we found that accuracy for that was very low, and making our model on our own and doing tweaking on the model will cost us a lot of time. So we planned that we need to either we can just make a final model and just go with it, whether we get low accuracy or high accuracy, we just need to accept it. or we can do one thing. We can find a model that has already implemented on internet, and they can it can do same task as the video human action classification on video. So for that, we have gone through a few research papers, and we tried to find a model which will be a less heavier on our model, which will be less heavier on our machine, because we had not access to a high computation power machine. So it was it was also impossible for us that we can run that Swinty model and MovieNet model in our computer. So we thought that as accuracy of Swinty model and MovieNet model was higher than 80%, we can just take original data, and that is also labeled like in Kinetic 600 data, there is also given a label that this video belongs to this class, and this video belongs to this class. So that we have chosen that as accuracy of our model is already Swinty and MovieNet model is already 80% or above, we can choose just we can just take original data set and we can train our model on it, because running that original model or Swinty or MovieNet in our machine and generate correct level for training data set, that would be impossible for us. So we have just downloaded the data and labeled data, and we trained our model on that data. And for that, we found a model on internet which was convolution LSTM model. And for that, we have used data augmentation, and first we need to convert input videos into sequence of images so that we can train our model on. And then after that, we can find output of what is the activity is happening in current video. So that is how we have proceeded for to solve the problem. But at this point also, we have tried to run that implement that model from online, but there was some errors, and we might not be able to resolve it. And that is how we have tried to solve problem. And here are slides of like, here is the structure of Swinty model. Here you can see that in the structure there is a lot more complexity. So, and we have tried to implement this Swinty model. We have tried to generate labels for from Swinty model, but it was too heavy for our machine, that we were not able to run this code on our machine. So we just accepted that we have to leave this, and we need to train our model on just original data set. And in model which we have taken from internet, that consists of bidirectional LSTM, and its hyperparameters are batch size is 16, number of epochs are 100, image dimension of each frame is 224 cross 224, latent dimension is 512, learning rate is 10 to the power minus 5. And here you can see a clip from a Kinetic 600 dataset. For black box, we aim to generate synthetic data from on our own, and we need to write a code for that. But that was first we were tried for gray box, but there was some errors at gray box only. So we think that first we need to focus on gray box only, and we have left we have leave that part of black box. So for gray box, we have planned to take 5% of each of Kinetics 400 or 600 data set, and then augment data and train it. We plan to split the data in the ratio of 80, 10, 10 on training, testing, and validation respectively. But what we actually did, we extracted 25% of data from Kinetic 600 and used 5% to extract it and made synthetic data by Kinetic 600 dataset. Now for training purpose, we have used first 20 videos on training and then five videos for validation and 5 as testing dataset. We trained our model on UFC 101 and for UFC 101 we have got accuracy around 41% to when we have tried to run it on our system. For training, we have used model structure of UCF 101. For training, we have used UCF 101 dataset, and we used categorical cross entropy as our loss function, and we have used Adam optimizer with learning rate, as I have mentioned, 10 to the power minus 5, and accuracy was taken as metric. We have for training, we have utilized power of transfer learning and used pre-trained ResNet model of 152. Used pre-trained ResNet 152 model with additional layers. In this work, we presented the usage of convolution LSTM for action classification task and harnessed the power of SwinT and MovieNet architecture. And we tried to assemble and run it on our system. And this gave us impressive results on our system on UFC 101 dataset. That is all from my side. Thank you. Hello.
Yeah, thank you. Like, why was it difficult to even load the model in the first place? Was it an infrastructure issue, or what exactly was it?
Yes, so you can see my screen currently right now. Yeah, right.
Yeah.
So here in SwinT model, they have implemented a heavy model which requires a lot of computation power. So that is the reason that we were not able to run it on our system. And that is why we were not able to generate labeled data for a training model. So instead, we have gone with just uh, original data set, because as accuracy was already higher than 80%, we can assume that original, so it is showing that almost labels in original data set is same as 80% same as generated by this model, SwinT model.
All right. Thank you.
Yes.
Yeah. No, I think thanks for the presentation. I think we got the idea. So thanks. No more questions from our side.
Okay.
Thank you.
Thank you.
Good luck.
Thank you, Team 1. You can now lower your hands. I request Team 5 to raise your hands so I can make you the presenters. Yeah, Team 5, do you have all your presenters here? Anyone
Yeah,
from Team 5 can reply. Are your members all here?
Yes.
That's fine. Okay.
You can start presenting your screen and let us know.
start. Am I audible?
Yes, we are.
Sure. Okay, so we're starting. So hi everyone, we are team 5 and we will be presenting our approach to the BOSCH model extraction challenge for video classification. The problem statement was, given a victim model as an API, we need to extract a new model that performs as well as the victim using only the ability to query it. By querying the victim and using its outputs, we can generate a new dataset to train an attacker model. This can be seen as knowledge distillation, where we do not have access to the teacher architecture or the training dataset. In the gray box setting, while we do not have access to any model architecture, we do have the power to use 5% of the training data that the victim was trained on, along with relevant datasets which are not part of the training dataset. These are used to query the victim model. In the black box setting, we do not have access to the victim model architecture or the data that was used to train it. We are also not allowed to use any data relevant to the victim's training dataset. Thus, synthetic data was the only possible choice for querying as evident in the figure. Let's now look at some of the dataset details.
So Kinetics dataset is a large-scale human action recognition dataset which contains around 4 lakh video clips. We have sampled 5% of this dataset for gray box setting. In black box setting for test set, we have sampled random 50% of the data and we used it as test set. Now we move on to data preprocessing steps. We first downloaded the required videos and extracted the frames at 1 FPS. And after extracting the frames, we have resized the frames to 224 cross 224 dimensions. And then to maintain a uniformity among all the frames, we have normalized all the frames to a value between 0 to 1. And after normalizing the frames, we have passed them into the victim model to generate the labels. Now we'll take a closer look at how frames were actually extracted. After downloading all the videos, we have sampled the frames at 1 FPS. But we found in most of the cases, number of frames were less than 16. So to get to 16 frames, we have duplicated equally spaced frames. Now let's look at gray box setting.
The approach is divided into two parts, a basic pipeline for this setting and finally an augmentation experiment added on top of it. The basic pipeline is shown in the slide. The data to query the victim API consists of 5% stratified kinetics data along with the UCF101 dataset. We chose UCF101 since it was quite popular among other activity recognition datasets and its videos were most similar to the ones in the stratified 5% kinetics train set. This was established by manually observing the videos from the two datasets. This mixed dataset was used to query the victim and its outputs were used to create training data for the attacker. We highlight a crucial contribution in this setting now. The attacker was trained in two phases. In the first, it was trained jointly on the kinetics and UCF datasets. After the validation accuracy stagnated, it was further fine-tuned using only kinetics data. We observed that since UCF101 was not from the same distribution as kinetics, a lot of the queries would not have been that useful. The two-phase training helped alleviate this problem a bit by allowing the model to first learn generic features as is done in pre-training, followed by fine-tuning to boost performance on the kinetics domain. Coming to the architecture of the attacker model, we used MARS, Motion Augmented RGB Stream for Action Recognition. It is based on a 3D Res Next 101 architecture. MARS takes only RGB frames as input, but leverages both appearance and motion information from them, thus reducing the cost of computing accurate optical flow, but having increased performance. Let's now move on to the augmented training setup. The query data obtained in the basic pipeline was further augmented consistently across video frames to increase the training set. The attacker was again trained in the same two phases. We used lateral flip, random crop, and blur as the augmentations for this process. Coming to the results, we saw a small increase in the top 5 accuracy on using augmentations, which is evident from the given slides. Overall, in the gray box setting, the results look decent enough given the amount of data that was available from kinetics that was stratified and was available for training. Now let's move on to the black box setting.
In the black box setting, we tried out 3 approaches: random noise training, data-free model extraction, and data-free model extraction using conditional GANs. These experiments were designed in a way to address the shortcomings of the previous experiment, and an increase in the top 5 accuracies was observed in our final black box experiment. Let us have a look at our random noise training experiment. We tried out 2 noise-based approaches. In the first approach, we used a brute force method to generate random training samples. These training samples are passed on to the victim and attacker model, and the outputs of the victim model are used as labels for the attacker model. Moving on to the random noise image generation process, the training samples were generated as random 4-dimensional tensors. A shortcoming of using such an approach was that the frames lacked temporal consistency. Here are the results for this experiment. The top 5 accuracies obtained indicate that the model was giving almost random outputs. So we tried out a different strategy to generate these random training samples using random rectangle generation. The shortcomings of this experiment were observed to be low confidence in the victim model's predictions, poor class diversity, and the generated samples lacked temporal consistency. In the random rectangle generation experiment, we generated rectangles of different colors. The motivation for using such an approach was that it has been observed neural networks view images as combinations of textures and blobs. Hence, in our approach, we generated training samples as shown. In order to maintain temporal consistency, frames were generated sequentially by perturbing the previous frame by a small magnitude. The generated noise dataset had a minimum of 5 images and a maximum of 10 images per class. The results for the random rectangle generation experiment showed slight improvements in the top 5 accuracy for the attacker model of SWIN-T. Yes. The random noise experiments fell short when it came to maintaining class diversity, getting high confidence predictions from the victim model. Hence, we designed our next experiment in the black box setting to overcome these problems.
The second method we implemented was based on the data-free model extraction paper presented at CVPR 2021. The approach involves training the generator and a tracker model in a modified GAN loop. The generator learns to create images that maximize the disagreement between the victim and attacker, while the attacker tries to adversarially mimic the victim as well as possible. Let's look at the generator we used. For the generator architecture, we initially used a modified video GAN with deconvolutions. It generated 32 frames of 224 by 224 RGB images in a single forward pass. Training this model proved to be extremely difficult due to the curse of dimensionality and the amount of GPU memory required by the model. To alleviate this, we experimented with single image generators like a scaled up version of a Cypher 10 GAN. However, even with extensive hyperparameter tuning, our approach did not scale up to this setting. Let's look at the results and the challenges we faced. These are the results we achieved with this method. A lot of challenges were faced in this approach, the symptoms of which boiled down to first, unstable training of video GAN, and second, poor class diversity. We experimented with a wide range of hyperparameters, tried to use multiple attacker architectures, and even image-based generators to stabilize training. However, in all cases, the approach did not work well. The generator fell into mode collapse, where it produced examples belonging to very few classes. Moreover, the victim outputs on generated images had high entropy and low confidence. Since the number of classes is huge, the generator is simply incapable of learning this complexity in a stable manner. Hence, we conclude that vanilla DFME approach does not work here. Our next approach was designed to overcome its shortcomings. We come to our third and most novel approach in the black box setting, using a conditional GAN with the DFME pipeline. To resolve the issues discussed above, we pre-train a conditional GAN ourselves with a data-free method to generate examples of the labels we provided. This generates a much more balanced data set. After the pre-training step, the rest of the DFME pipeline is exactly the same. Let's look at the pre-training in detail. The generator architecture is a scaled-up Cypher 10 GAN. The key difference is that a one-hot label is appended to the noise vector for conditioning the generator output. This pre-training step is entirely data-free and simply uses the black box model's outputs along with gradient approximation. No external data source was required or any external pre-training was required. Let's look at some of the generated samples. Here are some of the samples from the conditional generator. The visible difference from Gaussian noise shows that the generator has learned non-trivial features from scratch. We've also verified that the generator is not undergoing mode collapse within classes. The generator outputs had high confidence and were diverse over classes, which exactly solves the issues with DFME. Coming to the results, this approach gives us the best results in the black box scenario. It achieved a top 5 accuracy of 4.3% on Kinetics 400 and 3.7% on Kinetics 600. There are 3 reasons for this result being much better than the previous results. It can be attributed to the fact that the generated samples had high confidence and were diverse across and within classes. The training was also more stable for the image-based generator compared to the video-based one. Thus, these gave more signal to train the attacker and prevented immediate mode collapse. Now, let's look at our adversarial experiment.
We now come to an interesting experiment that we tried in order to increase the query efficiency. In the adversarial targeted attack, we used random noise as images and observed that most queries were classified in 5 to 10 classes. To generate diversity among the outputs for training the attacker, we hypothesized that using a targeted adversarial attack would be helpful. Here is a pipeline for the experiment. A target class is chosen that should be given as the output by the victim model. The input image is first perturbed on a random pixel and channel by adding a constant epsilon. The output is then queried to check if the victim model's output is the target class. If yes, then the image is kept on. Then the image is worked on for further iterations, and if not, the epsilon is subtracted and the process is repeated. If this method does not work out, a new pixel is sampled and the process is repeated. We found that scaling up this approach for videos was extremely difficult. Hence, we resorted to images. While this did give pretty good results, it took approximately 40 minutes to perturb a single image and hence did not scale well. We can explore other approaches for such attacks which can be computationally less expensive in the future, as training GANs can be a difficult process in general and even more so with videos. The experiment demonstrates a very promising alternative approach. One can use both random noise and random rectangles as seed images, which further demonstrates the robustness of this approach. Moving on to the challenges faced and our solutions for the same.
First, datasets are very large in the order of 100 GB. So downloading the datasets and pre-processing them is computationally very expensive. So to tackle this problem, we have pre-processed the datasets and used them for testing and training. Second, training and fine-tuning GANs parameters is a difficult task. On top of this, training time was very high, which limited the number of experiments we could run. We have used grid search to fine-tune the GANs parameters and added a noise at the start to prevent the discriminator from outliering the generator. Moving on to the conclusion. So finally, we conclude that in black box setting, data-free model extraction plus conditional GAN gave best results. Although adversarial experiment gave good results on smaller dataset, we weren't able to scale it to larger datasets. And in gray box setting, Mars model with augmented training gave an accuracy of around 65%. Moving on to the future work. In future, we would like to explore adversarial attacks more. As already said, they gave better results on smaller datasets, so we would like to extend it to larger datasets. And second thing we would like to do is investigate more on video GAN methods, as due to computing limitations, we weren't able to run many experiments in this area. Moving on to the relevance in industry, this problem is quite relevant in the current industry as to prevent the malicious attacks. Model extraction helps understand the model architecture better, which helps industries to build more robust models and also safeguard against these attacks. Any perception API provided by BOSCH needs to be safeguarded against these kind of attacks, as it can cause huge revenue loss and make them more vulnerable to further attacks. So with this, we conclude our presentation, and we would like to thank the BOSCH team for giving an opportunity to work on this interesting problem. Thank you.
We are now open to questions. Thank you.
Hey, hi. Firstly, I think a great presentation and good approach, and thanks for also putting the last caveat of protecting BOSCH, our APIs. So nice input there. So I think a really nice approach. I just wanted to know what were, let's say, your top, let's say, a couple of challenges that you might have faced, and secondly, like if you have to work on this problem, let's say for another month, right? What would you change or what would you do differently?
So one input is that a very big problem in this problem statement is we do not have access to the victim's logics, and instead we have access to the final predictions. So that changes a lot in terms of how well we can train the attacker model. So that is one thing that we felt was a major challenge in the problem statement. Secondly, the GAN we need to experiment more with the hyperparameter tuning in the GAN training. So we believe that if we are able to train a good generator, then we can see significant improvements in the black box setting.
And just to add to that, we faced a lot of issues when initially we tried with generating videos. We tried with video GAN, but like in this setup, it's extremely difficult to scale it up to videos. I mean, training a single GAN itself is quite challenging, and like if you extend it to videos in this DFME loop, it becomes very unstable. So that is something we would need to investigate. We need to look for approaches to stabilize that training. So which is exactly the reason why we resorted to images, since we were able to debug them more easily. So if given a month, we would like to explore that part specifically more, because since it's a video based setup, that is bound to increase performance.
Got it. Thanks. I think. Thanks, team. Team, I have a different kind of questions. If you can go back to your data free model diagram that you have used. There. And my threat model is a little bit different. So while you move there, is that you have a continuous feeding to the teacher model. Yes, here the victim model, and you are getting the output. What if I say that you can generate as much data as you want, but I'll give you one single try to pass through an entire data to victim model, and after that I will cut you off? What would be your approach in that case to train your attacker model? You only get a one shot, but you can have as much data as you want.
I mean, off the top of our head, one of the experiments we tried, which maybe showed some promise, was that rectangle generation thing. So if Shubhnil, you can just show that rectangle slide. So I mean, if you just have to query data, and if it's a black box setting, of course, you're not allowed to use reliable data sets, as it was mentioned in the problem statement. So so here, if you just go back to the previous slide. So our intuition here was basically that any neural network would look at these images in terms of these blobs, right? Textures and blobs. So inspired by this, we tried to approximate this sort of an image to understand what, like basically saliency maps would also look something like this. So we tried to understand what the network would predict given such images. So I mean, we would definitely include images like this in our data set for querying in the black box setting, because this is like the closest approximation to what an neural network visualizes internally. So yeah, I mean, apart from any other noisy data, or since we are queried only once, maybe we have to make the best out of the single query and then analyze the results. So like this data would definitely, the intuition behind this experiment was specifically like this. Like we wanted to.
Understood. Understood. Just to paraphrase, my understanding is that if you go to the previous black box, it's a uniform kind of distribution, and you really don't know that how the contours and the other patterns will be recognized. But if you use a kind of a squares or any other kind of an abstract pattern, your intuition is that the system will able to pick it up, or the neural network will able to pick it up those kind of an abstract boxes, which can help to go little better. So going from the uniform distribution to some informed distribution, which is closer to the real world. Is my understanding correct of your answer?
Yeah. So instead of extremely random noise, there is at least some structure in the data you're giving to the model, and that structure is inspired from these saliency maps.
Okay. Can you now go back to your? I just have one final question, and that is on the gray box. Can you just go back to your gray box data picture, please? Yep. Now, you say 5% of kinetics trained data, and you have used the UCF 101 trained data. So this is the combination that you have used. And here again, what I see is that you are again using this kind of a mechanism where you are continuously learning about that what the victim model is giving. Here also in the gray box, if I give you only one shot, you can have as many data as you want.
Now here we have not done it in an online setup. We've collected all the data, generated all the logics, and then used everything offline. So it's not an online setup.
Okay, and here you use the labels or the logics?
The logics.
Okay,
logics. I mean the outputs of the victim model.
Okay. Just to make it clear in my head, was it the probability or just the class or both?
No, just the class, just the
class. Yeah, argument.
Yep.
Fine. And that's all from my side. Any other question?
I have a question in your adversarial data generation. So the block diagram that you have, is that already generating data, or are you proposing that we could generate image data?
So
Go
we
back to
cannot
your
give
slide.
certainty that the model will learn best from training samples that look like real world images. This
So have you used image data generation already, or are you generating video right now? For your
no,
grey
we
box
are using image generation right now, but using GAN-based approaches. So instead of using a GAN-based approach, the adversarial attack approach shows promise because it's easier to train, and yeah, that is the.
How do you ensure temporal dependencies between your images?
No. So right now for the adversarial setup, so yeah, just to put us everyone on the same page, since video was difficult, we also tried to obtain the accuracy, top 5 accuracy with images on Swinty, and without with videos it was 86%, with images it was 65%. So it was not that bad a drop. So we thought that since image training can be more stable, we decided to go ahead with images for GAN-based training and adversarial as well. But yeah, I mean, for the adversarial experiment, it was more of a proof of concept to see how can we better generate data to query and reduce the number of queries. And so we resorted to images since it was much faster and easier to train for the time being.
All right. Yeah, got it. Thank you.
Thank you. Thanks a lot.
Thank you.
I think no more questions from us. I think great job. So all the best.
Thanks a lot.
Thanks a lot.
Yeah, thank you, Team 5. You can now bring down your hand. I'll ask Team 13 to raise your hands, please, so we can identify. Yeah, Team 13, I see only 2 people raising their hands. Is that it from your team? Team 13, can you just confirm it?
Hello, are we audible?
Yeah, you're audible now.
Okay, so there are only 2 people who will be presenting today.
Okay. Okay. As I'll just remind you, people, after 13 minutes of your presentation, there'll be a bell ringing. So you're left with just after that bell ringing, you're left with 2 minutes for your presentation to end.
Okay,
It's
sure.
just a reminder. Thank you. Continue.
It feels like one of our team members is experiencing some issues with the audio, so I'll be continuing.
Yeah, it's fine.
Okay, so welcome everyone. Good morning. We are Team 13, and we are here to present for the BOSCH model extraction attack for video classification. So let's briefly discuss about the problem statement first. Basically, we are given a model which we don't know about anything like what's its internal architecture, what it has been trained on, and we have to replicate or extract this model into a different model that was mentioned to us as a part of a problem statement. So in this, we were given 2 data sets, Kinetic 600 and 400, and we were given 2 settings. The first one was black box setting. In this setting, we have no prior knowledge about the relevant data sets that the model was trained on, and we cannot even use the relevant data sets. Instead, we can use some synthetic generated or irrelevant data sets to this setting. Okay, and yeah, as I already mentioned, we have to use an architecture that is different from the victim's architecture. For the victim architecture, we are referring to the Swinty model and the MovieNet model, as we'll discuss later. And in the gray box setting, we have no prior knowledge about the model's internal architecture, but we may use the original 5% of the data that the model was trained on, along with the synthetic and generated data set for training the model. And as with the black box setting, we have to use an architecture which is different from that of the victims. Okay, so here are the victim models. First one is the Sven Tiny model, and the second one is MovieNet A2 based model. Okay, so how did we approach this? Basically, we based all of our approaches on the DFME, the Truong et al., the data-free model extraction approach. And since in the paper this was a methodology which was applied on images, we had to adopt it to the video domain. So basically, what it does, it samples a latent vector from normal distribution, passes it through a generator to generate input video, and then passes it through victim and student models and tries to align the logics of these two for this thing, for the input videos, I'm sorry. Okay, so how does it do this? So since we only have black box access to the victim, we can't just right away backpropagate through the victim. So in this case, what this paper does is it uses gradient approximation method, which is forward difference method, and approximates the gradient to train the generator. Okay, and the key challenges that we faced to adapt the DFME approach to the task was that we had to choose a generator which could generate 3D videos and a victim model which could process 3D video, which could process videos. Okay, so firstly, let's discuss the generator architecture. We adapted the generator which was introduced in the VideoGAN paper, and we had to like add some transpose convolution blocks so that we could get the appropriate sized inputs to be inputted to the victim model and our student model. Then the choice of the student model was video vision transformers. This was made due to the recent success of transformer models on the task of action classification. Okay, and the approach for black box setting was we basically took the DFME and the components that we discussed before, and we put them together and we trained our black box. So we generated videos using the 3D generator, then we passed them through the SwinT model and the MovieNet model, and then we use the student model of video vision transformers, and then we use the loss formulations in the DFME paper, which was basically L1 loss, to train our generator and the student models. And approach for gray box setting, actually we couldn't make this happen, but I would really like to mention the approach that we planned. Okay, so we plan to initialize the generator from the video GAN, which would have been trained on 1% of the training data, and we would have used the rest 4% of the remaining data to distill the victim model into the student model. So these two sets would have been disjoint, as if there were any common videos in them, the student model would have easily learned to cheat. Okay, so for the results, and actually I'd like to mention that we had some issues while downloading the test data. So we were only able to report these results on like around 1200 of images, 1200 videos. So these are our results. And for these, we used a query size of around 20 million. And the parameters are listed for the video vision transformer models as visible. And here are some of the challenges that we faced. Okay, so the approach that we discussed, DFME, it requires a huge amount of computational power. So we had to use a V100 GPU of 32 GB with a batch size of 4 to train our approaches, and that too required a lot of time to converge. Okay, and that was the reason that we could not make the gray box to converge due to time constraints, and the GAN training was a bit unstable on our side. And the third issue that we faced was the issue related to the gathering of the data. We had throttling issues as we used a large number of threads to download the videos. We weren't able to get the videos as the YouTube denied the access for due to throttling issues, and the network latency was also an issue during our setup. And this is a scope for expansion. Like if we were given any additional time, we would firstly review more literature on the gray box setting, and we would use a different generator, maybe DVD GAN based generator for the student model. I'm sorry, for the generator model, and we would also like to try some 3D CNN approaches for the student model if you get enough time. And yeah, that's from my side. Thank you very much.
Team, thank you. It was a great presentation. I have one question.
Yes, sir.
You only tried the black box. Is my understanding correct?
Yes, sir.
Okay.
That's correct.
That's correct. Any reason why you didn't try the gray box?
Sir, actually, we had some prior academic commitments in this semester, and we also weren't able to make the generator converge using our approach. And I would like to admit that we weren't able to also explore the wide literature that is available for the gray box settings, and yeah, we lagged on that front a bit.
Okay, great. Now, when you say the gray box, can you just go back to your results page? Sorry, black box results page, please.
Surely, sir.
In both of the cases, you have your student thing, which is at 22.83 and 25.4 million parameters, and you use the VBT for that.
Yes, sir.
How many queries that you have utilized?
20 million, sir.
How many?
20 million.
20 million. That means you generated 20 million video clips.
Yes, sir.
Okay. Understood. Understood. Great. Do you have a sample of how your generated movie clip looks like
We are
from your
sorry, sir.
transformers?
We are sorry, sir. Actually, we tried to generate that, but we had issues with the storage on our system.
No, can you just show me one of the clip if you have any?
I'm afraid, sir, I don't have any at the moment.
Okay, understood. Yuvraj, you have a question?
No, I have no questions. Mine was also related to the number of queries.
Amit?
Like team, firstly, thanks for the work. Very interesting. I mean, do you think, let's say, you have more time, let's say your team has been told that only work on, let's say, black box, but let's say you want to achieve these results with, let's say, lesser amount of queries. Do you think it is something that is possible, or so after you have done this, do you first of all have some kind of a heuristics to know that, okay, if a model is, let's say, of X parameters, then I would need X queries? Like, have you built some logic? If you're, let's say, you have been told to do this on a different victim model, would you now have a better idea of how many queries you might need? I mean, just give me your approach, basically.
Actually, sir, we would certainly like to try out some numbers, but we base that we won't require as much queries as we have used now. We have realized that we could also do this using a lesser number of queries, maybe around 1 million or something like that, or even less than that. So we would obviously consider parameters, something like parameters by 20 queries or parameters by 40 queries.
Okay, let me ask this the other way around. So this 42% accuracy, at what query number did you already reach this?
Sir, we used 20 million queries for this.
You don't have intermediate heuristics.
Achha, so you don't have intermediate heuristics, if I understand. Like, did you run it from like 0, 10 million, 15 million, 10, 20 million?
No, sir.
So they generated 20 million just right now.
Okay. So I think purely out of this, I would also just explore if you do like an intermediate one and just see when you actually reach this, right? You might have reached this much earlier if you had done some intermediate versions.
Sure,
Check it
sir.
out.
We'd like to try that. Thank you very much.
And final question, this is top 1 or top 5 reported?
This is top 1, sir.
This is top 1, is it?
Yes, sir, but it is only on 1200 videos, as we were unable to gather all of them.
What is your top 5 accuracy in black box?
Sir, top 5, we haven't really calculated them, sir. We thought we were only about to calculate the top 1 accuracies.
Okay, understood. Can you circle back to us with your top 5, please? If possible, or you will not be able to do it in the short span.
I'm sorry, sir. Sir, we would definitely like to try if we could do this, but we're really not sure about the resource utilization that we have currently available.
Understood.
We would like to try that. Okay, sir.
Okay.
Even otherwise, it would be interesting to see one video clip that was generated from this video game.
Okay. I think this is good enough from our side. That's all.
Thank you very much, sir, for your time.
Thank you.
Good job, team. Thank you.
Thank you very much.
Thank you. You can now lower your hand and stop presenting your screen. Nakul, you can stop presenting your screen. Right. All right, judges. So this was the last presentation for the morning session. It was scheduled from 9 to 12. So we'll take a break now and we'll resume the session at 2 with team 8 starting their presentation.